Hello again. In this video we're going to talk about vectors in equilibrium. Now what vectors in equilibrium are, and here's a good diagram to represent it. Say for instance you had something you wanted to suspend from the ceiling, like a chandelier or something to that effect. But there was something right above it and you couldn't anchor it in there. Say you had to have two different cords coming down suspending this chandelier or whatever it happens to be. And it was a 100-pound chandelier, and this cord created a 40-degree angle with the ceiling. This cord created a 20-degree angle with the ceiling. Another form of force is tension in a rope or cord or whatever. So we're going to call this cord 1. So T1 represents a tension in cord 1. T2 represents a tension in cord 2. This is our real-world diagram. We're going to go from that to a vector diagram, like we discussed before, where now the length of the vector is representative of the force, or the magnitude of the force. In this case, the magnitude of the tension. So all three of these chords meet at this one point. That point is here. We then have a 100-pound vector going straight down. That's the weight of the chandelier. And we have T1 going off at a 40-degree angle to the horizontal, T2 off to a 20-degree angle to the horizontal. What we're going to do here is we're actually going to solve for the length of T1 and T2. Because remember, the length of the vector, again, is representative of the magnitude or the numerical value of the vector, or how many pounds of tension are in that vector. So what we're going to do is we're going to separate each of these three vectors from this point. We're going to rearrange them to form a triangle. Because the past couple modules we talked about right and oblique triangles and how to solve for sides and angles. And remember now the lengths of these vectors that will become the sides of a triangle are again representative of the magnitude of the force in that tension. So we arrange them, we put the 100-pound vector straight vertical there. And if it's a vertical vector, and all weight vectors are, it's perpendicular to any horizontal. We're then going to take T2, and we're just going to slide it right here at the same angle. It's like rearranging pieces of a puzzle. T1, we're going to slide and put it right here. So now we form a triangle. And again, we have one side of the triangle, we're solving for the other two sides. The angles, for instance, T2 is at 20 degrees to the horizontal. It is still at a 20-degree angle to the horizontal. But since this 100-pound vector is perpendicular, if you have 20 degrees outside, there's going to be 90 minus 20, or 70 degrees inside. Likewise, with T1 tacked on here, it's still 40 degrees to the horizontal. So if you take 90 minus 40, that gives you a 50-degree angle to the horizontal. To clean it up a bit, I just drew the triangle with a 100-pound vector there, a 100-pound side, 50 degrees there, 70 degrees there. Remember, all three angles of any triangle always add up to 180. So you take 180 minus the sum of these two, which is 120. You have 60 degrees here. You now have a matched pair. Matched pair, if you think back to oblique triangles, automatically think of law of sines. So we're going to use law of sines to solve for both T1 and T2 separately. So we have the sine of 60 over 100 equals the sine of 70 degrees over T1, which is what I have right here. So we have our sine of 60 over 100 equals sine of 70 over T sub 1. Remember, to solve in law of sines, you have to cross multiply. So T sub 1 times the sine of 60 is going to equal 100 times the sine of 70. To get T1 by itself, you have to divide both sides by the sine of 60. Those cancel out, and T1 would simply be equal to 108.51 pounds. So basically it's 100 times the sine of 70. Don't forget to close the parentheses after the 70, divided by the sine of 60. That gives you 108.51. So that's how much tension is in chord 1. To get T2, we're still going to take our sine of 60 over 100, but now that equals the sine of 50 degrees over T sub 2. So writing it out, sine of 60 over 100 equals sine of 50 over T2. If we cross multiply, T2 times the sine of 60 will then equal 100 times the sine of 50. To get T2 by itself, divide both sides by the sine of 60. And if you type that in, 100 times the sine of 50, all divided by the sine of 60, you'll get 88.46 pounds. Now, you may be thinking, well, this is only a 100-pound chandelier. Take the sum of these two, you get almost 200 pounds. Thing is, if you had one cord suspending that chandelier, it would only have 100 pounds of tension in it. However, what makes more tension in the cords are the angles that they are to the horizontal. So whenever you stretch out that angle, it takes more tension because you're not just working in a vertical motion. Now you're adding a horizontal component. So you're going to need more force or more tension in that cord to support that same 100-pound weight. So this is a good example of how to use vectors in equilibrium to solve for tension, and actually using vectors to solve specifically a force vector for tension in a cord.